My name is Alan Baratz. I'm the CEO at D-Wave Quantum. It's a pleasure for me to be here with you all today, and thank you all for taking the time to participate in this event and join this session. You've heard a lot about quantum over the course of the last few hours, but almost everything that you've heard about is related to only one architectural approach to quantum computing. That's called gate-based or gate model quantum computing. Is what literally everybody in the world is working on when they're working on quantum computing. We at D-Wave are building gate model quantum systems as well. But there is another approach. It was discussed briefly in one of the panels earlier today, and that's called annealing quantum computing. And D-Wave is the only company in the world that has developed annealing quantum computers. And they're quite unique in the sense that there are a broad array of very important business and governmental problems that they can address. And they are addressing them today. That's why when you watch that video, you saw a whole host of use cases or applications that are in flight today. So we don't talk about you will be able to do, or in 3 years you will have this, or in 5 years you will have that. That's all true when it comes to gate model quantum computers. But when it comes to annealing quantum computers, they are truly commercial today. Customers actually using them today as a part of their business operations. The area that I'm going to spend a little bit of time talking about is aerospace and quantum use in optimizing a variety of different aerospace applications. But before I go there, I just wanted to give you some perspective on the quantum industry. The last 12 months have been very interesting, very exciting, and very important for the quantum industry, both from a commercial perspective as well as from a technology perspective. Commercially, we have seen the first quantum applications actually move into production. I talked about this a minute ago. Customers actually using quantum computers to support portions of their business operations today, and I'm very proud to say that that's being done with D-Wave quantum computers. In addition, it's expected that in 2025, almost 50 quantum computers will be sold across all of the quantum computing companies, but 50 quantum computers sold. If we look at the independent public quantum computing companies and their market cap, it has grown roughly 2,000% over the course of the last 12 months, from a combined roughly $4 billion in market capitalization to where we are today with over $40 billion in market capitalization. And analysts covering publicly traded independent quantum companies has doubled within the last 12 months. Technologically, we've seen the first true demonstration of quantum supremacy on a quantum computer. When I say true demonstration, what I mean is this is being done on an important, useful, real-world problem that can be solved in minutes on a quantum computer and would take millions of years to solve on the fastest supercomputers in the world. And again, I'm proud to say that this work was also done on the D-Wave quantum computer, the first and only example of quantum supremacy on a useful, real-world problem. We've also seen important advancements in the gate model space. The Google Willow announcement was groundbreaking. This was the first time that anybody had actually demonstrated a prototype for a logical qubit, and they were able to demonstrate that error rates went down as we moved from physical qubits to logical error-corrected qubits. It was done on a small scale, but it was the first time that we ever have seen a logical qubit built and seen error correction improve the quality of the qubits and the gates. We've also seen significant advances in the quality of qubits and gates across a variety of different quantum companies, depending on the underlying technology, anywhere from 99.9% fidelity to 99.99% fidelity, so making good progress on improving the fidelity of qubits and gates. And new error correction technologies have been developed to simplify and make it more effective and cost-effective to do error correction on quantum computers. So it's been, as I said, a really interesting period of time for quantum computing. At the same time, it's been a really interesting year for D-Wave. We launched and made generally available our 6th generation quantum computer. We call it the Advantage 2 quantum computer. It is the largest and most powerful quantum computer in the world with over 4,000 qubits. Yep, I said 4,000, not 400, not 350, but 4,000 qubits. It is the quantum computer on which supremacy was demonstrated. It is the quantum computer on which we are supporting commercial applications. We also demonstrated how you could take that supremacy computation and use it to create a new blockchain that uses quantum proof of work. So what's so important about this? First of all, quantum proof of work is quantum safe by construction. So we don't have to worry about, for example, Bitcoin being broken because of the crypto capabilities of quantum computers. This would be a quantum safe blockchain. If Bitcoin were using it, it would be a quantum safe Bitcoin. But secondly, far more energy efficient. We're talking about, frankly, being able to mine Bitcoin using 1/1000th the power of what's being used today if you were using this quantum proof of work. We've seen advances in leveraging our quantum computers to do AI, and I'll talk more about that when I get on the quantum AI panel a little bit later, and significant advances from a commercial perspective with respect to bringing new customers on board and system sales. But I'm supposed to be talking about aerospace. So in the last few minutes, let me spend a little bit of time talking about that. This actually all began at Quantum Beach 2 years ago down in Miami. So I was on a panel talking about quantum applications, and one of the executives from Boeing was on the same panel, and he basically said, "We've tried quantum, it's not ready for prime time." And I challenged him. And we got into a little bit of a thing, and the moderator of the panel said, "Okay, you should take this offline," which we did. We've made a lot of progress since then across a variety of different application areas with a variety of different customers. Everything from airplane production scheduling, where different tasks, different materials, different skills, different dependencies, and you've got to reduce the time to assemble a plane by doing the work in the right order, right? Called reducing the make span, where leveraging our quantum computers, we're able to show significant improvements and compute the schedules much faster, to materials design for new components. Typically, this is done using classical heuristics and AI, and once again, we're able to show that leveraging the quantum computers, we can create much more viable components using the right materials. To facilities placement. I mean, where do you put the manufacturing facilities in order to ensure that you can get the parts to them when you need to get them there without excessive costs? We've also worked with the German airport to optimize gate assignment for a better traveler experience. We've worked with GE Vernova on how you can optimize repairs for large airplane engines. And we worked with Unisys on cargo loading and how to optimize the cargo loading process to both speed it up and put more cartons within a single container to essentially reduce cost. So a lot of progress in the aerospace industry as well. So I'm really excited to be here today to be able to share with you the progress that both the industry and D-Wave has made over the course of the last year, along with some of the really interesting work going on in the aerospace industry. With that, I'm going to ask Matt to join me up here for the last 2 minutes.
Thank you so much, Alan, for that. So, you know, one of the biggest things that we are talking about here today is obviously workforce development. And what are some of the things that D-Wave is doing with universities? I think it's really incredible.
Yeah, so we have a broad set of relationships with a number of different universities, both in the US as well as up in Canada. Frankly, a lot of the work we do today with the universities is around fabrication. So we use superconducting technology in our quantum computers, which means we need to fabricate processor chips using superconducting materials, which requires new materials, new processes. And so we work with the universities on discovering new materials and discovering the new processes with respect to how to do that fabrication.
So with AI, is that impacting you guys in some ways of attracting talent?
No. So first of all, quantum is very exciting broadly, but students that are coming out of university, whether it's undergrad or graduate school, have kind of chosen the areas that they want to work in, and we are not seeing any challenges with respect to hiring people that are interested in working with us. But they are not trained properly to work with us. So we basically train them on the job. They want to be in quantum. They've got a good, solid engineering background or a science background, in some cases a business background, but they don't know enough about what we do to be able to be effective day one. And it can take up to a year to train them. So one of the things that we are starting to focus on is how we can work with the educational institutions to get better quantum programs in place so that the graduates can hit the ground running.
And one of the things that we are going to get into in a little bit on another session when we're with President Ava Parker is the college level, meaning we need a more broader spectrum, and if you can kind of highlight that a little bit at not just a higher university level, but also at a college level.
Yeah, as I said, it's not just PhDs, masters, it's undergrads as well. We hire across a broad array of disciplines at all levels. And, yes, we have, 50 PhDs that are part of D-Wave. We have a workforce of about 300 right now. But that means we have 250 that are not PhDs. And, it is critical that we have the proper skills graduating at all levels.
Well, with that said, Alan, thank you so much
Thanks,
for
Matt.
coming here today. Guys,
My
thank
pleasure.
you.